Okay, I'm going to start this with the TV screen and my wheels. Here's the big wheel, which shows the north rotating that way. They're both rotating to your left in the front, and the south is rotating that way. And they're both rotating to your right in the front. So it's all rotating in one direction, which is what my small wheel shows. Same thing, let me turn it that way. Arrows in the same direction, arrows in the same direction, and arrows in the same direction, if you see. Okay, so there's not a problem there. My little wheel is the same as my big wheel, if you get me. And what we'll do, we'll put the north to the screen of this magnet. Let it come back on. So it's going to be rotating to our right. Twists to the right, correct? Back to the left, to the right, let's go. To the right, let's go. If I turn it the other way with the blue towards the screen, it twists to the left. To the left, because the red's towards us now, the blue's away, so it twists to the left. And I can turn it any way you wish. The red to the left, the blue to the right, it goes down in the back, if you see. And if I switch that, well, let me just put that in there. Down in the back, see that's up in the front, down in the back. If I turn that up in the back, down in the front. So back there, it's going up. Okay, so it's all true what I said before, and we'll move on. Okay, the first thing that happens, what you need to know or should realize and understand is no matter what I do with the magnet in the right or left-handed coil, no matter what pole's doing what, the charge moves the same no matter what. I can't change that, okay? So one of the first things I want to show you is I'm going to put the south end forward motion, right-hand coil, and move it forward. I get a positive reading. Did you see it? Back I get negative, forward I get positive. But if you notice, with this orientation, the magnet is rotating its magnetic field opposite the winding of the coil. So why does forward show positive through the coil that way? Was positives coming out the back of the coil, negatives coming towards us. Positives, a charge moving away from us. Negatives, a charge moving towards us. Same on the left-hand coil. So when I pull the south back, I get a negative. Push it in, I get a positive. But the rotation of the magnetic field, according to the TV screen, is opposite than the coil. So it's like it's contradicting itself, okay? Now if I flip the magnet over, now it's rotating this way in the same direction as the coil, like that, same direction. When I push the blue in, I get a negative. It comes towards us. And when I pull the blue out, I get positive. So the south pole in the right-hand coil, the charge follows direction of motion. Motion in, positive charge. Motion in, positive charge. Motion out, or negative. I'm sorry, motion in, negative. Motion out, positive. Motion in, positive. Motion out, negative. Okay? And let me put the north on the other side. Same exact result with the north though. Motion in, positive. Motion out, negative. Flip the magnet. Motion in, negative. Motion out, positive. So the south pole of the coil in the right-handed, or south pole of the magnet in the right-handed coil, from either end, it follows the motion of the magnet. On the left-handed coil, the north pole follows the motion of the magnet. The charge follows the motion of the magnet, okay? The charge follows the motion of the magnet on both coils, with the south to the right and the north to the left, wound coils. Okay, now when I put the north into this coil, if you notice, it's wound in the same direction as the coil. The magnetic field is rotating in the same direction. However, when I push it in, the charge comes back. The magnet has to swallow the charge. And when I pull it out, the charge goes away. The charge goes away from the magnet. I can do it again if you want. push it in, the charge comes towards the magnet, pull it out, the charge goes away. Back here, when I push it in, the charge goes away from the magnet. When I pull it out, the charge goes away from the magnet. Or I'm sorry, when I push it in, the charge goes over the magnet swallows the charge. When I pull it out, the charge goes away from the magnet. Same thing. Push it in, the magnet swallows the charge, pull it out, the charge goes away. And this end, push it in, the magnet swallows the charge, pull it out, the charge goes away. And notice the blue did the opposite. So the north on this side, the right-hand wound coil, the motion, the charge moves opposite the motion on the right-hand coil with the north. With the south, the charge moves with the motion. Even though in both orientations, the rotation is in the same direction as the coil, but when I push it in, I get reverse. And over here, when the rotation is opposite the coil, I push in, I get reverse. It's like the rotation direction is opposite than what the coil reveals, what the charge direction reveals. It always seems to reveal opposite. The forward motion on the north over here is a reverse action. The forward motion of the south over here is a following action. But the rotations are opposite. You would think, since the rotation of the blue here is against the coil, it should swallow itself. Going with the direction, opposite the direction of the coil, it should go backwards to the coil. It does not. It goes forward with the coil. And the north is the opposite. When I push in, it comes back, even though the rotation of the magnet is with the coil. It's always reverse. Now, I'm going to show, well, let me move to another point. Same thing again on the outside. Now, if you notice, out here, the coil is wound this way, going down on the outside, the right-handed coil. So if I put the south forward, the rotation of the magnet's also going down. So they're going in the same direction. The magnet should be pushing the charge with the coil since it's rotating in the same direction. But if you notice out here, when I push, the charge goes backwards. The magnet has to swallow the charge. And then when I pull, it goes forward, away from the magnet, like the north did on the inside. The south is doing on the outside, but the north does on the inside. That same thing happens over here, but reverse. What the north does on the inside, the south does the opposite or does the same on the outside. Even though the directions of rotations of the magnet and directions of windings of the coil are opposite each other on both occasions. And I can put the south on this end, where I turn it around. Now the south is coming up on the magnet over here, right? And the coil is going down. So they're in opposite directions. When I push in, the charge goes that way. The magnet has to swallow the charge. And when I pull it out, the charge goes negative away from the magnet. So take a minute and contemplate that, because this side does the same thing this side does, just reverse the poles over here. So contemplate that. On this side, opposite directions of rotation, the charge follows movement, positive, negative. And with the south on this side, reverse the direction, south going in, it reverses again. Negative, positive. I mean, the charge follows the flow, the direction of movement with the south and the right-hand coil. And the charge follows the motion of the pole of the north pole on the left-handed coil. Negative, positive in, negative out. This will be negative in, positive out. They reverse each other if you reverse the poles. And like I said, when you put the magnet in the same rotation as the coil, again, it reverses. Push the north in, the magnet has to swallow it. Reverse direction of charge movement. And on this side, if I push it in, positive, reverse direction of charge movement. So now, if that's a paradox, the motion of the magnet in the ways I'm explaining with this rotation, and even if the rotation has nothing to do with it, why does it do that in opposite rotations? You would think that if it's just the field itself, it should follow the direction. Is that not correct? Look at this. if the south is in there, and it's just a field, and let's get rid of the rotation of the magnet. Let's just go with the winding of the coil. When I push the south in, I get a positive reading. Push it in, positive reading. The field forced the charge to go with the winding, okay? And on this side, when I push the south in, the field forced the charge to go backwards through the winding. That makes sense. But there's no rotational properties here, okay? Let's forget about the rotation of the magnet, just worry about the field that's out there. Why is it when I put the north in and I push, the charge comes backwards? And on this side, when I put the north in and push, the charge goes backwards. And like I said, everything reverses on the left-hand coil, pole for pole. And what I'm saying is the rotation has got to have something to do with this. Otherwise, the north should do just like the south, and it should follow suit. Push in, positive. It's not. It's negative. And on this side, push in, negative. It's not. It's positive. It's as if the magnet has went all the way through. But it doesn't work that way. Push the south in, positive. And over here, if I pull the north out, it goes negative. So even if the magnet went all the way through the middle of the coil, it still reverses as soon as the magnet gets halfway through. Okay? There's a reason that does that. I'm showing you. It'll be positive going in and then negative when it comes out. Positive going in, negative coming out. Like I said, north on that side, negative coming out. Everything is reverse. The direction of rotation of this is opposite the direction of windings of the coils, and the motion is the same with south in and south out on the red coil, or south in and south out on the red right-handed coil. And the north, the motion and direction is the same north in and north out on the left coil, or north in, north out on the left coil. So think about that a little bit. And when we get to the next part, I'm going to show you my rendition of how to fix this paradox, and it works. It works, it works. I'll prove it, and we'll go to the next part. Before we go to the next part, I wanted to show this, though. I showed you the outside, like the north is rotating up, the coil is rotating down. We should get a negative charge, but we get a positive. If you watch, push the north in, positive. The north outside of the pole is rotating up, the coil is going down. You'd think the contradiction there, you think it would go with the motion of the magnet. It does not. Or it does. It goes with the motion of the magnet, even though the rotation directions are different. And vice versa with the south. I showed this a while ago. I'm going to show it again. Vice versa with the south forward. It's rotating in the down over here on this side. If you see that, down on this side. And the coil is rotating down, twisted down, threaded down. So when I push in, it goes negative. The magnet swallowed the charge. And when I pull out, it's positive. The charge went away. And it does the same thing on this side, and it reverses on that. I showed you that. Something else I wanted to show you was from the side over here. If you notice, when the magnet comes in, it's kind of at an angle. So you see that it's coming down. It's coming down. Hang on a minute. Where the magnet is coming to the coil, it's coming up. I'm sorry, it's coming up. And when it comes up, I get a positive reading. But you would think, coming up, it should shove the charge backwards through the coil and get a negative reading. But it doesn't. It goes on with the direction of motion. With the direction of motion. Now, when I get over here, on this side, which is odd because that's moving in the opposite direction, if you see what I mean. It's coming up, should shoot the charge backwards through the coil, but it doesn't. It goes with the thread of the coil. Now, when I get on the far side and go away, it's positive. Go away, it's positive. Even though the magnet now is going down, it shows positive. Or negative, I'm sorry. This side shows negative, even though the charge is going down on the magnet at this angle. If you see that, which should be with the coil to give us a positive reading, but it doesn't. It goes negative. Coming in goes positive, and you think it'd be negative because it's coming up. See that? It's coming up to the coil. It's the same thing this way. Push it in positive, pull it out negative. Push it in positive, pull it out negative. Same thing, I'm just showing it to the outside. On either this way or this way, it shows the same. But it's reverse. The direction of rotation of the magnet is in reverse orientation to the threading of the winding of the coil, but the charge moves opposite than the rotation direction of the magnet. Okay, now we'll move on to showing you why this paradox happens. Okay, we're back at the TV screen, and I'm going to fix the paradox. You're not going to believe me, and I'm not afraid to admit when I'm wrong. Isn't that what science is all about? When you're wrong, you admit it, you see your mistake, you figure out why you were wrong, and you fix the problem. So this is what I thought, what I showed you before, the magnet was doing. The south to the screen rotates to the left, north to the screen rotates to the right. Okay, like that or like that. This is wrong. It is wrong. Why? Compression. Compression. So what we're going to do, you're not going to believe me, you're going to say this is preposterous. What we're going to do is reverse the direction that I said magnets rotate, and we're going to reverse it. The south, this way, is actually rotating the opposite way. Okay? And the north is rotating the opposite way. I know, this is preposterous. Well, what needs to be done or understood, in my theory, the magnet, when it's magnetized, is feeding in from both ends. That is why everything wants to stick to the end. This is just a steel ball. It's not magnetized. It doesn't stick there, but it does to the ends, both ends. This is feeding in both ends. So there's a longer distance for the gravity to go from both ends to feed this all the way to the center. It's not spherically radial, all the way around going to the center, like most things that are not magnetized. And beyond that, it's spiraling as it goes in. So you've got a long distance from here to there as it goes that way and that way, plus it's spiraling, okay? So it's like you're going through a coil to get there. Takes longer, so you have to speed up to get there in the same time that the atoms need their feed as if it was not magnetized. Hear me out. So the only way that the ether can do this is by compression. There has to be compression out here to force that charge in a spiral to feed these atoms. The spirals slow down in the middle and cancel each other out to normal gravitational speed. That is why the ball does not stick in the middle. See, nothing. Here, I gotta pull it off there, all right? So, that's why it has compression. The point is, the magnet is rotating opposite, but the compression is backed up. It's a backup of ether charge. It's backed up, and you're seeing the backup. When you go into it, the backup pushes it away, and when you come away, it releases. Like eddy currents work in the same operation. I have a video on eddy currents, which is perfect, but it shows where I thought the rotation was my old version, like this, and it's not. It's the other way. So my eddy current video is right, just the direction of rotations in that are all reversed. That's all it is. So if you've ever seen a wheel on a bicycle or wheel on a car, if you turn it at a certain speed, you see it rotating in a certain direction. But after a while, if you speed it up, then it starts to look like it's rotating in the opposite direction. And that's like flashing, reflecting off of it, hitting your eyes with the shutter of a camera makes it look like it's moving in the wrong direction than what it actually is. This is doing this because the ether is backed up to force the charge to go in the correct direction of rotation. I'm going to prove this in a minute with the coils. We're going to go back to the coils, and I'm going to prove this. So it's reverse of what we think. The magnet's actually rotating to the left in this orientation. This is my new wheel. It's reversed, okay? The magnet's rotating in the reverse direction of what that box moves. If I flip it over, it reverses again. That is because it's just like the ether works like fluid dynamics and gas dynamics. If you have a pipe and you want water to be pressurized in that pipe, you have to have compression of water. Let's say we're not using a pump. What could we use? A water tower. You have to have compression of the water in a huge volume down into a smaller volume to pressurize the line to get it to go where you want it to go, where it needs to go. And air or gases work the same way. If I take my air compressor and just run a hose off the piston, it takes forever for it to fill the line up and fill a tire up. It takes 15 minutes to fill up a little 30-pound tire, just holding it there. But if I put a tank on my air compressor and let the pistons fill up that tank with some volume, so compression, then I can fill that tire up in just a few seconds. That is the same thing that a magnet is doing, the ether is doing, the dielectric is doing to the magnet. It's compressed out here, but these little electronic signals in the TV are getting pushed back opposite the direction of rotation because of the compression. They're compression. The iso potential lines are back compression lines. Like I said, this is rotating opposite. It's rotating that way, but the compression shows it reverse. And I'm going to prove that here in just a minute. So when the magnet moves forward, a push, you get compression, but it's in the reverse on the TV screen. And when you pull away, it releases on the TV screen. But I'm going to show you with the coil, it's actually what the magnet is doing, which is reverse of what the TV shows and the electric arc. My electric arc experiment showed the same thing, but it's actually reverse. And I'm going to show you now, or prove to you now, that that is so. Okay, now I'm going to prove to you that I'm not crazy. Remember my old direction of rotation? It's this thicker wheel, wider wheel. I'm going to set it to the side for a moment. This is our new one. Reverse rotation to what the TV screen shows. And when I start working with this, it'll make perfect sense, I believe. Or it should anyway. I'll adjust this up just a wee bit. Hopefully you can still see the charge. Positive, negative, positive, negative. And now what we're going to do is put the blue magnet pole, north pole or south pole, into the right-handed coil, which is wound the same direction, which is reverse of my earlier diagnosis or conclusions. Reverse. So it means it's the rotation of this magnet is actually rotating in the same direction as the coil. So when I push it in, it goes with the rotation of the coil. The rotation of the magnet goes with the winding of the coil, and the charge moves away. Now, what gets freaky is that back charge, the back pressure of the ether. When I pull it out, the reason it goes negative is because it's filling in where the magnet is retreating. So when I push, the rotation goes through. But when I retreat, the backfill of the ether follows reverse of the magnet. Reverse in direction and reverse in rotation. That is why the charge follows the magnet in both directions. The magnet's causing that with rotation and motion, and the ether causes that with rotation and motion. The magnet is not causing the charge to follow it. Same this way. Now, I've turned my magnet around. I'm going against the winding of the coil. Okay? The rotation of the magnet is against the coil, so when I push it in, I should get a negative reading. And I do, because it forced the charge to go with the rotation. The rotation of the magnet and the winding of the coil are in sync. This way, they're in sync. If you see what I'm saying. This way, they're in sync. It moves with the motion. This way, they're in sync. it moves with the motion. Makes perfect sense. Now, and when I pull out is because the ether is coming back. You can call it eddy currents, you can call it what you want. The dielectric is coming back and the magnet is retreating, so the dielectric is filling in reverse of what the magnet did. Now, to prove it further, we'll put the north in, which is rotating opposite the coil, okay? And when I push the north in, the charge comes back. The magnet had to swallow the charge. The charge went against the motion. That's because the rotation was against the direction of the winding of the coil. The rotation followed the coil, not the magnet. It followed the coil. Okay? And when I pull out, the retreat was reverse. If you notice, it's rotating that way, but the retreat and the ether coming in will be the opposite way, which is the same winding of the coil. So when I retreat, I get a positive reading. It goes away from the magnet. Okay? So rotation is key here. But the other key is that the ether reverses whatever the magnet does. And it depends on direction of motion of the magnet. Coming in, it went opposite because it was rotating against the coil, so that it went backwards through the coil. Pulling out, it's retreating, so the ether came back in with the direction of the coil. I hope you get this. This side does the exact reverse. The north is now winding with the coil, but when I push it towards us, I get a positive reading. The rotations are in the same direction, and the motion doesn't matter because the rotation of the magnet and the winding of the coil are overpowering the direction of motion. They're overpowering the direction of motion, if you get that. That's why that does that. This side, it goes backwards because the rotation is against the winding of the coil, so the coil just lets it go backwards through it because the rotation. I'm leaving, the ether comes in and pushes it backwards against it, against the direction of rotation of the coil. And it works the same on the left-handed wound coil, but you reverse the magnets. You can check that out yourself. So let's go back to the outside now. Same principle. Now this time, with the south out here, the magnet is coming up. If you see that, I guess you can see it. The magnetic field is coming up against the coil. The coil is wound going down in a thread. The magnet is turning up. That's why on the outside, when I push the magnet in, it has to swallow the charge. Up here, push the magnet in, has to swallow the charge. Everywhere on the outside, it has to swallow the charge because the rotation direction of the magnet coming up on this side now is opposite the coil. Now, if I put the north over here in reverse direction and the rotation of the magnet is with the coil, the charge will go positive, see? Positive. In reverse setting, pull it out, negative. The ether came back and made the negative. The ether came back and made the negative. This way, when the ether comes back on the south, it goes positive because it's coming back and running down the coil the other way. It's like the coil is threaded. The magnet can make the motion of the rotation go with the threads, but it has to be in the same direction. And it has to be in a forward motion. The forward motion of either pole follows, if the magnet's rotating in the same direction as the coil, the charge will follow motion. If the magnet's rotating in the opposite direction of the coil, when you push now in a forward motion, it'll be reverse, okay? The winding of the coil follows direction of rotation. On a push, that's only on a push. On a pull, when you retreat, the ether determines. When it comes back in, flyback, it's like flyback. The flyback reverses what the magnet did. It follows it out like a spring, and it just reverses direction of rotation. The magnet pushes it in, the flyback follows it out. That's what I said. The push follows rotation of the magnet, which is reverse of what I first thought. The pull is not the reverse of the rotation of the magnet, it's the ether coming in and filling back in opposite the direction that the magnet rotated it out of the way. So I hope you get this. It works. And you can try this yourself. If you reverse the rotation of the magnet to this, where with the north away from you, it's rotating counterclockwise. With the north towards you, it's rotating clockwise. It's opposite than what my other experiments show. It's back pressure, it's flyback, it's the ether being displaced from compression because the magnet is fed from both directions linearly and in a Fibonacci spiral. There has to be compression here, and it's backed up, which shows opposite results on a TV screen and such. But this proves it does follow the rotation of the magnet, and the ether counteracts that exactly opposite. Let me know your thoughts.